This is from section 6.3, number 2, and here we're given this rational function, a polynomial on top and the polynomial on the bottom, and we're asked to integrate. And the first thing we're asked to do is write the integrand with this partial fractions decomposition, and then afterwards integrate it. So this is the hardest part, and then hopefully we get the integral into something that's much nicer to integrate. The first thing we notice is that the numerator, the top, is a polynomial of degree 3, and the bottom is a polynomial of degree 4, the denominator. Since the degree on the bottom is bigger than the degree on the top, we don't need to do polynomial division. But we do need to factor this denominator. So I'm going to rewrite this, this fraction, 9x cubed plus 10x squared plus 125x plus 150. X to the fourth plus 25x squared. And I'm just going to rewrite this factoring the denominator. So the numerator I'm going to leave alone. And this denominator factors kind of nicely. I can just factor out an x squared. And I've got x squared plus 25 left over. Now when I look at this, x squared plus 25, I can't reduce that anymore. I can't factor that anymore. So this is an irreducible quadratic. X, though, is a linear function, a linear term, and there are two of them. So I know when I do the decomposition, I'm going to have something over x plus something over x squared, because I have two terms, two linear terms repeated. And then I'm going to have something over x squared plus 25. Now, when I have a linear term like this, I can have like an a or a b constant. But if I have a quadratic, an irreducible quadratic, it can't just be a single constant. It's got to be a constant times x plus another constant. I don't want to use b again. I should use a different one. So I'll use d. And I see this looks exactly like what we've got right here. So they knew that the decomposition was going to look something over x plus something over x squared plus something over x squared plus 25. Now I made the a, b, c, and d match up here, but if they weren't matched up, you could switch around the variables. Okay, so our goal is to figure out what a, b, c, and d are, looking at this right here. So what I'm going to do is I'm going to rewrite this this expression right here. I'll give myself some space down here. But I'll need to figure out what a, b, and c are. Alright, so let's see. I'll rewrite this exact fraction. 9x cubed plus 10x squared plus 125x plus 150 over the x squared times x squared plus 25, which is the same as this. And I know that this is the same, and I'll rewrite this, but I'll leave some space, as 9 over x plus, I'm sorry, not 9, a over x. I don't know why I made that a 9. A over x plus b over x squared plus cx plus d over x squared plus 25. But as you can see, I've left a lot of space there because I want to get a common denominator. And that common denominator is this one right here. So what does x need to have this same denominator? It needs an x and an x squared plus 25. So I'll put that on the top and the bottom. Notice I haven't changed this a over x. I've multiplied it by 1 in a way such that I'm going to get this same common denominator. What does this term need? Well, it already has the x squared. It needs an x squared plus 25. And again, I'm going to multiply that on the top and the bottom. Because I know I want it to be b over x squared, but I got to figure out what I need to get that common denominator. This last one, I'm going to put these in parentheses so I make sure not to make a mistake here. And I need to multiply this by x squared on the top and bottom. Okay, now comes the algebra part that's really kind of intensive. I need to multiply all of these terms through. The denominators are the same, because I know this and this are the same, and the denominators are the same. But now I have this 9x cubed plus 10 x squared plus 125x plus 150 equals whatever I get when I simplify all those numerators. Alright, so let me bring this 9 through here. I'm sorry, I keep on calling it a 9. This a through here, ax times x squared would be ax cubed, and ax times 25 would be 25ax. Let me bring this b through to both sides. That'd be plus bx squared plus 25b. And let me bring this x squared through to both sides. That would be, let's see, this x squared times cx would be cx cubed, and x squared times d would be dx squared. Okay, now I've got all these terms, and I need to somehow figure out what my x cubed terms are going to be. Here are all my x cubed terms. What my x squared terms are going to be. Here are all my x squared terms. What my x terms are going to be. Here are all my x terms. And what my constant terms are going to be. Here's my constant terms. So I'm going to have a different equation for each of those scenarios. For the x cubed, how many x cubes do I have on the left side? Well, I've got 9 x cubed on the left side. On the right side, I've got ax cubed plus cx cubed. So if I look at just the x cubed elements, 9 over here has to be the same as a plus c over there. I'm going to do the same thing for the other ones too. X squared, I've got 10x squared over here on the left. How many x squareds do I have over here? Well, I've got bx squared plus d. Let's see, how many x terms do I have? Well, I've got 125 x's on the left, and it looks like I've got 25a x's on the right. Finally, for my constants, those terms without any x's, I have 150 on the left. Over here on the right, I have 25b. Now this is a system of equations with 4 equations and 4 unknowns. So I should be able to solve it. It probably has a solution. And this one ends up being kind of nice. The first two, or the last two equations turn out pretty nicely. Let's see, for instance, what would b be to make this true? How many quarters do I need to have $1.50? Well, I would need 6. So b would equal 6. Similarly, how many 25s would I need to have 125? Well, a would equal 5. Sometimes it requires a little more work to get these, but these ended up being quite nice. Now I can plug this one over here. 9 equals, well, a is really 5, so 5 plus c, so c must equal 4. And over here, 10 is equal to b plus d, but b is really 6, so d must equal 4 as well in this case. So if I go back up here to where I started, right, what are these a, b, c, and d's that make this true? Well, a must be 5, b must be 6, c must be 4, and d must be 4. So what I've done is now I can rewrite my original integral like this. It's the integral of a, which we said was 5, over x. So this is that a over x, that a over x, that a over x. So a is really 5, plus b over x squared. Well, what did we say b was? We said b was 6. Plus cx, so cx would be 4x plus d plus 4 over x squared plus 25. And the whole point of all that algebra, we haven't done any calculus so far in this problem, the whole point of all that algebra was to turn this challenging integral into this integral that's broken up into partial fractions, which hopefully is a little bit easier. Well, let's see if we can figure this out. This integral This one's not too hard. This is 5 times the natural log of the absolute value of x, because this is 5 over x. Okay, plus I'll take this 6 out right here. The antiderivative of x to the negative 2 is x to the negative 1 divided by 1. So this would be the same as over x, but I should change that positive to a negative. Again, the antiderivative of x to the negative 2, just in case you're wondering where that's coming from, is, well, it's x to the negative 1 divided by negative 1 plus c. So I can write that as negative 1 over x, and there's the 6 that's still there. Now I still have the rest of this. This doesn't lend itself to an easy u substitution yet, but what I can do is I can write this rest of it as the integral of 4x over x squared plus 25 dx plus the integral of 4 over x squared plus 25 dx. Now for this integral, I can use a u substitution. For this integral, I'm going to have to use my arctangent information. Okay, so let's finish that up. So I'll have to get a whole other piece of paper here. For the integral of 4x over x squared plus 25 dx, well, I'm going to do a u substitution where u equals the bottom, x squared plus 25, and du would then be 2x dx. I almost have a 2x. I have a 2 hanging out here, so I'll take out that 2, and I'll have 1 over u du. The 4x is really, so this 4x dx is really 2 times 2x dx, and this 2x dx is really my du. So this I can integrate. This is 2 times natural log of the absolute value of u plus c, which is 2 times the natural log of the absolute value of x squared plus 25 plus c. But in this case, if you did forget about that absolute value, you wouldn't be wrong, because x squared plus 25 can't be negative. Okay, so there's that integral. The last integral we need to figure out is this one right here. So let me write that integral again on this piece of paper. This is the integral of 4 over x squared plus 25 dx. Now, you might have a formula memorized for arctangent. We know that the integral of 1 over 1 plus u squared du is arctangent of u. And you might even have a formula memorized that looks like this. The integral of 1 over u squared plus a squared du is something. Now you can have that memorized if you want, but even if you don't have that memorized, we can do a little bit of algebra to figure this out. I'm going to take that 4 out, and we'll have 1 over, and then what I want is I want this to be a 1 here so I can use this formula. So I'm going to take out this 25. And what I'll be left with is x squared over 25 plus 1 dx. And now I can take out that 4 and the 25, and I have 4 over 25, the integral of 1 over, and this is x over 5 squared plus 1. Because x squared is this x squared, and 25 is 5 squared. And I can do a little u substitution where u is 1/5 x, and then du is 1/5 dx. Because this is what I have right here, I want this to be my u squared. I want to use this formula right here. So when I look at that, I need a 1/5 dx. So I'm going to take one of these 5s. I've got 2 5s down here. So I've got 4 over 5, the integral of 1 over u squared plus 1 du. Because I'm going to take one of these 1/5 and these dx to make that du right there. Finally, I can plug into my formula. My formula right here says this is, well, there's my 4/5, and I've got arctangent of u plus c. But u is really x over 5, or 1/5 x. At this point, you may have remembered that this formula right here is 1 over a arctangent of u over a plus c. And if you have that one memorized, it makes it so you don't have to do those little substitutions. But we've done that. Okay, finally we're ready to put it all together. So all these integrals together. If you remember, we already did these two, and then we wanted to know what this one was and this one was. So let's put them together. The first one, if I want to integrate, was 5 times the natural log of x. Okay, so I'll write that one up here. 5 times the natural log of the absolute value of x. The next one was this minus 6 over x. Okay, so I'll put that up there, minus 6 over x. And this next one was this one where I had to do a u substitution. Let's see what that one was. When I did that u substitution, it ended up being 2 times the natural log of x squared plus 25. I'll put the plus c at the end. And the last one was this arctangent one. And we just did that arctangent one, and we saw that it was this 4/5 arctangent of x over 5. So plus 4/5 arctangent of x over 5. And then finally, after all that work, I put a plus c. So there's a lot going on in that problem.